Okay, we're going to get started. I have a couple of announcements. The first is that during the break, which will be at almost exactly 3:20, we would like to have a group photo. So at the beginning of the break, if we can go outside the building, the photographer will be ready, and we'll have a building. Not a building. This is a building. We'll have a photo. And then a quick plug from Jim Head. The climate history of Mars was the early Mars climate, warm and wet, or cold and icy. And he's actually giving a talk here tomorrow, 1 till 2, during the lunch break in the Hess room. If people would like to attend, you're very welcome. And with that, for the first talk this afternoon, the Hypanis Fluvial Deltaic. Oh, why do I get the hard titles? Lacustrine system in. Yep, Terra. Then thank you. This is why you went to here. And the talk will be given by Jacob. Actually, we've been asked you to point at the map, the big map over there. Go and point where your easy is.
All right.
Yeah. While you get mic'd. Maybe your co-speaker could point at the map. Oh. That wasn't embarrassing at all, was it? No, there we go.
Testing.
I didn't see the photographer.
Oh, did you already point?
I pointed.
So
Okay.
you'll get a 5-minute warning, and then you'll feel a presence after about 2.5.
All right, good afternoon. My name is Jacob Adler. This is Melissa Rice, and we're presenting. We'd like to first thank our co-authors, especially Sanjeev Gupta and Elliot Sefton Nash, who could not be here today, and our other authors who've worked on this. I'd also like to thank the steering committee for a travel award, which allowed me to come here and present. So, our exploration zone is called the Hypanis Fluvial Deltaic Lacustrine System. And what we see is that we have 2 deltas within our one exploration zone, which is quite unique. We have Sabrina Delta and Hypanis Delta, both Mars 2020 candidates, past proposed missions. So in the regional context, we find that Hypanis Delta is situated north of Valles Marineris, south of the Crissy Basin, and right here we've marked where the Crissy Escarpment is. And here we see Sabrina Delta and Hypanis, and this is where the Hypanis Vallis flows in and then deposits the delta. What's unique here is that the delta is deposited into what looks like Crissy Basin, which has very large implications for a global key question about how much water was there on the surface of Mars, and was there a Crissy Sea? I'm going to quickly run you through all of our ROIs. In blue we have our science ROIs, and in orange we have our resource ROIs, which Melissa will talk about. So to start out with, our first 4 ROIs are our deltaic units. We have Hypanis Delta, an extra lobe, these 2 fingers, which are inverted channels which come out of the Hypanis Delta lobe. Our ROI 5 is Sabrina Delta, and 6, 7, and 8 are channel units which expose a vertical stratigraphy in the deltaic plains unit and Hesperian plains unit here. ROIs 9 and 10 and 11 are in Liederberg, actually. 10 and 11 are on the rim. 9 is where there's possibly some volcanic cones, and 12 and 13 are also exposures of bedrock. Finally, 14 is where we have a contact with ejecta. Melissa will talk more about the landing site, the ISRU capabilities, and resource ROIs for posterity. Here is a geologic map created by Peter Fodden. We see in blue our deltaic mapped units. In green, some plains material. In brown, crater rims and highlands. In white, some of these ancient Noachian smooth buttes, which are probably eroded crater rims. And in yellow, finally, we have the crater units. So our ROIs sample a full diversity of the units within our exploration zone. Here is our rubric, and what I want you to take away from this are a few key points. We have a big potential for past habitability. because we're looking at a deltaic environment. Deltaic and lacustrine environments, according to the Summons 2011 paper, are the best environments for preserving, concentrating, and forming organic matter. Also, we have access to both Noachian bedrock and Hesperian units. We have clear evidence of aqueous activity, and we address a major global question of was there a Crissy Sea? Here are some of our ROI images. You see Hypanis Delta. This is what the surface morphology looks like in some cases. We have potential for past habitability, aqueous processes, stratigraphic contacts, outcrops which range from Noachian to Hesperian, and later Amazonian units. We have, again, deposits which have a potential for containing organic matter in the delta. Here we see some cool high-rise views, especially when we look at a 2 times vertically exaggerated view. This side view shows the wall of the delta units. We could likely sample some rocks that fell down the slope and are collected in the talus at the wall of this cliff. Here we see some more pretty pictures of these well-developed sedimentary layering on the side of the delta. And we know exactly where the fines versus the coarse grains would be and where the organics would be in a delta environment because we've studied these extensively on Earth. Again, a very cool side view of the delta stratigraphy, which is accessible to us. Another interesting feature is this lobe, which comes out of the delta. It's, again, a very large system, and Melissa will talk about its scale relative to the other deltas on Earth. Some interesting perspective views, which I'll let you look at later. And finally, the Sabrina Delta, which is quite unique to have 2 deltas and 1 ROI to sample. And here's an interesting side view showing deltaic strata, contacts to take materials from and sample, and the polygonally fractured basin floor materials. With that, I'll hand it over to Melissa.
Thanks, Jake. Hello? On? There we go. Okay, so as Jake showed, we have spectacularly preserved stratigraphy in the Hypanis Delta and the Sabrina Delta system. But I want to point out what's really exciting about these features, which is their larger context. So these are not deltas that have formed in small normal Martian lakes. These are deltas forming along the edge of the Crissy escarpment, which is also the Martian dichotomy boundary. So we have the possibility here to sample deltaic sediments that might have formed in huge bodies of water here. And also the catchment, the sediment source region for these deltaic units is huge, enormous, sampling a large variety of materials, Noachian materials in the southern highlands. So the next ROI I'm going to show you is within the Hypanis Vallis channel. And this is an interesting site because it's right along the dichotomy boundary. Here, the Hypanis Vallis system has dug a natural road cut into the dichotomy boundary for us to observe the stratigraphy. So we have an ROI here where we observe multiple bedrock units being incised and easily accessible to our astronaut explorers. The next ROIs are within Liederberg crater, which is in the northwest portion of our exploration zone, and these allow us to sample a larger diversity of crustal bedrock materials and potentially igneous materials. So Browse and Halber in 2013 have a paper proposing that some conical features within Liederberg may be hydrovolcanic features, such as these seen here. And regardless, this is a great hypothesis for astronauts to test within Liederberg about hydrovolcanic activity in this larger region. Or if these aren't volcanic cones, then this gives us a chance to look at some interesting crater morphologies. We also have some interesting bedrock units along the rim of Liederberg. These have some indication of layering and are likely Noachian crustal bedrock being exposed. Finally, we have several fresh impact craters within the exploration zone, and these allow us to explore a variety of crater morphologies and impact structures. And we have clear identifiable contacts between these craters and multiple units. So here's another example of some crater floor morphologies in a crater in the northern part of our exploration zone. Moving along to the resource potential within the Hypanis EZ, we have really narrowed this down to two classes of resource ROIs. One which is in the immediate vicinity of the landing zone, and two which are targeting hydrated mineral sources as possible water resources. So these are the distributions of our resource ROIs on our geologic map. And the first resource ROI has a nice cluster of our water, mineral resources, and our civil engineering resources, all within 3 kilometers of our landing site specifically. So we have our landing circle indicated here, a proposed location of a resource processing plant, and a field station, all within very close proximity and right next to where we would land. The other 2 ROIs are locations where there are widespread hydrated minerals that have been detected by CRISM. So these serve as additional water resources for us. So here's that first resource ROI showing the vicinity of our landing area. The landing circle is to the north, just about 1 kilometer off of the site on a nice flat bedrock plain. And we're proposing a potential field station that could exploit the natural topography here. This is a natural depression with a nice cliff face that could potentially help us in building a structure that would shield from radiation and also weather environments. We also have very close to this landing vicinity a very extensive dune field. And so our proposal would be that these dunes themselves would be our major resource. And so as was presented in Fred's discussion of Gale Crater, the early discovery by the Curiosity mission was that the sand dunes at the Rocknest site had 3 to 6 weight% water in the sands themselves. And so these sands that are ubiquitous in our Hypanis exploration zone could be a great water resource, and this is very easily mobilized material. The dune fields that are close to the landing site at Hypanis, dune fields that are close to the landing site here are very extensive. They do not have many indications of induration, such as craters, and so that suggests that they are easily scooped up and mobilized and could be heated and also used as a metal resource and a silicon resource. So here's where we would propose a processing plant, which would be on firm bedrock, easily traversable, right at the edge of the dune field. And this black square here, this is showing the size of that US football field from the supplemental paper, which is the area that would be required to excavate at just 10 centimeters depth for 3 weight% water. Nice perspective view here again shows the resource processing plant, which could be positioned on hard bedrock with easy access to an enormous resource of this sand material, 9.2 square kilometers within just 3 kilometers of this processing plant. But for those who like hydrated minerals, we also have those. CRISM has detected large exposures of magnesium and iron-rich clays within our exploration zone, so we have a couple of these sites indicated as potential water resources as well. So in terms of the data needs for a Hypanis exploration zone, CRISM FRT data is really the limiting factor in a lot of our analyses and why we have not focused on hydrated minerals as the primary source of a water resource. So we would propose 3 locations here where clays have been detected in CRISM MSP images that would be great places to target with CRISM FRT for higher resolution and better spectral data. We also have images that are in the pipeline for ExoMars and Mars 2020 landing site efforts, but these are additional locations that could be used for exploration, for understanding our exploration possibilities as well. So in summary, the Hypanis Delta is a fantastic environment for potential habitability, indicating a long-lived large body of water and potentially a crisis sea. Deltas are also fantastic for astrobiological preservation and concentration of organic material. Our exploration zone has key stratigraphic contacts between all of the ROIs, and the diversity within this site is really widespread. So this is really would be a site that would best take advantage of a human exploration mission. There are things, some of the best things about this site, a rover simply could not do because of the aerial extent of our diversity in this EZ. The resources here are very extensive and very easy to mine, and there are natural building materials and locations where we could take advantage of natural topography to build as well. And then finally, the science implications here are really global, really getting at the big questions for Mars. What is the nature of the dichotomy boundary? And what is the nature of long-lived bodies of water and potentially seas, not just lakes, but seas on Mars? So these are some of the big questions we think that human astronauts will be able to address at this site. And that is it. Thank you.
Thank you, Melissa. Thank you guys very much. By the way, I'm Lindsay Hayes. I presented to you guys about your polling cheats and everything yesterday, so don't forget to fill them in. Just wanted to introduce our next presenter here. Jack Mustard is going to be talking about the Jezero Crater Watershed, Isidis Basin, Sulfate Deposits, and Syrtis Major. And while I'm reading the rest of your title, will you go over and point at where your site is?
Not as well as Melissa.
A compelling exploration zone for human exploration.
It's a fantastic place. Like that.
Check, check. Are we up? And the pointer and the clicker. There they are. All right, Jezero Crater Watershed in the Isidis Basin. Next to the Isidis Basin, the sulfate deposits. Next to Syrtis Major, it's got an incredibly compelling suite of reasons why human exploration would be in an enjoyable place for many years to come. Here's the broad scale overview of the area, and I'll show you on a global map, but here we are on the edge of the Isidis Basin. This is the exploration zone in a large hoop, and then within that there's any number of science ROIs and resource ROIs, and quite frankly, I could just put a big blob on the whole thing and say it's a science and resource playground across the whole area. Of course, you're not going to believe me. I'm going to have to show you what I mean by that. Here are 3 sites that we're going to look at later on. First one being the Jezero Crater Delta itself, this large zone in the middle, the Nili Fossae Plains, and then down into the extensive sulfate deposits at the bottom for resources. Here it is in black and white, if you prefer that than the topography that I had previously. And you can see it looks really rugged. Like you're like, how are we going to land here? But quite frankly, as we've looked at this for Mars 2020, it's actually quite safe to land at that 10-kilometer scale. And it looks rough, but it's actually pretty easy to go through. So why do we want to go here? There's compelling Mars and astrobiological science that make this really important. Bedrock strata in situ representing 4 distinct environments, aqueous environments, of aqueous alteration where reactants and products are together. These are 4 of them there: early crustal, carbonate, serpentine, layered phyllosilicates, and sedimentary sulfate formation. There's compelling data. There's the compelling delta of the Jezero Close Basin Lake, which has a fantastically preserved delta with 4 set beds and a prograding delta that has among the highest priority sites for preserving organic matter. There's a record of aqueous low-temperature geochemistry preserved in situ in mineral-bearing strata, distinct in age. We have spectacular, well-preserved stratigraphies from Noachian and Hesperian, which are datable surfaces that we can collect samples from. And there are multiple igneous units of distinct age. So this chart here is meant to go through the threshold science criteria along this side, just taken from the report, and where we would get to go and do all these things within the science ROIs within the landing site, within the exploration zone, so it's not a landing site. And I don't necessarily want to go through all these. I'll leave this behind for you to go through, but I think we target all these exceptionally well. And that's why I say it's going to take more than a decade, I think, of exploration to do these analysis once we get there. I put this up here. This is the summary chart from the Mars 2020 landing, second Mars 2020 landing site workshop. I put this up here because the rubric, we went through an extensive rubric exercise in this activity, and these are the areas of that we're focused on: the landing site scientific criteria, geologic setting and history, was it an ancient habitable environment, biosignature preservation potential, astrobiological quality, and petrological quality of return samples. So here are the 21 sites that were looked at this meeting. And why do I put this up here, right? Because I want to show you 2 things. One, Jezero, which was the top rated through this set of criteria. It's not the same as what we'll be looking at here. And then the northeast Syrtis. Those were sites 1 and 3 through this analysis, and what we're doing here with this exploration zone is putting those two together, because we've got 100 kilometers, we can fit them easily together. So it says that there's been a community-wide evaluation of this site, which has come out in a fairly high evaluation aspect. Okay, so let's look at it a little bit more. Here is essentially the site is located here. It's between the first and second ring of the Isidis Impact Basin. We're in a pretty important place if you want to understand planetary evolution and formation, between two rings of one of the last impact basins formed on this planet. And that really sets up the geology of the region and why it's interesting. Here we're going to go look at a little closer in terms of where are we in Mars geologic time and what can we look at in here. So here's the Amazonian through Noachian and pre-Noachian time scale on the bottom, time along the bottom. And these are some of the major mineralogic evolutionary events from the Phalosian or neutral pH period of clay formation to the sulfate formation in the middle period. What's great about this site is we fit right at that boundary. All the geology that we care to look at is right at that boundary, in which we have, in here, this line marks the Isidis Impact Basin, in which was emplaced an extensive olivine-bearing unit, which has resource potential and also huge scientific implication. Associated, past that moment in time, there are these series of geologic formations that occurred, which have distinctive mineralogic signatures which are associated with those units. So that's the fact that we have the mineralogic units in place where the reactants and products are together. And it's not one, it's not two, it's not three, but there are at least 4 of those in there. So this is really exciting that you have a lot of exciting opportunities to evaluate the region. Okay, so I'm not going to go through this in detail, I'll leave it behind, but there's at least 6 to 7 big-scale testable hypotheses with which we could address by getting those samples and examining them in great detail and really understanding the geologic history and formation. So let's look at science region 1, which is at the Jezero Delta. So it's in a Paleo-Lake basin, which addresses these key areas. It's got sedimentary carbonate and iron magnesium smectites, which shows the standing body of water with circumneutral pH. This is the delta itself. I'll show another view of it, in which the colors are representing the mineralogy as mapped by the CRISM instrument. And then you've got spectacularly well-preserved sedimentary layering, which gives the evidence that it's a deltaic and lacustrine sedimentary environment. Here is then another overview of it, and the delta itself is here. And this shows the watershed which fed the 2 deltas, a western delta and a northern delta. And then this is the 2 inlet valleys which feed 1 outlet valley. So that's that has a standing body of water over a period of time to create this setup here. This is a geologic map that's created, so it's been very well studied. This is Tim Gouge's work to put together this detailed geologic investigation. And what I'm going to say now, we're going to look a little bit closer at the delta itself. Here it is in terms of safety of landing. This is actually a safe place to work in. This is the western delta itself. We're going to look a little more closely. Here we got the northern delta, some of the preserved aspects of it. And then the western delta is over in here. We're going to look a little bit more closely at this now because I want to show you the evidence of the layering within that delta and what it's telling us about the surface. Here is in the western delta in a perspective view, like Melissa showed or others showed for the Hyponus delta. And you've got beautifully preserved bottom set beds and then the foreset beds. Bottom set beds are, from astrobiological potential, really exciting exploration targets because it's the bottom set beds that are deposited in quiescent water, which could capture any organic material that may exist at that time. There's another view of a different perspective which shows the foreset beds coming in as well, which gives us really clear indications that this was a delta in a standing body of water. Let's move on to ROI Science ROI 2, where we have olivine and carbonate and the evidence of ancient crust. Another, just to show that there's been extensive geologic mapping in this region. And the topographic map that shows there's this depression in here, but we're going to stay up here on the plains for the moment. Extensive CRISM data around to give us detailed mineralogic understanding of the region. But what I'm going to show you then here is that we have a cross-section from the Syrtis Major lavas. Again, that's one of these age-datable units. Syrtis Major lavas, cross-section in here, which then shows us that we have the basement of the iron magnesium smectite bearing basement, which also has pyroxenes. On top of that is this green unit, which is olivine and carbonate. So it looks like it's an olivine unit that has been variably altered to carbonate. And then sitting on top of that is this 500 meters of sulfates. And as we talked about yesterday, which I sadly missed, but is the importance of polyhydrated sulfates as a source of water. So these are not, we know for a fact that there's at least 2, but likely 4 water molecules per sulfate, per sulfate unit in here. So it's got an abundant water source going on there. Okay, this is now tapping into the most ancient part of Mars that we can get to. This is the megabreccia. I put this up there. This is within the exploration zone. And it looks like a mess, right? But I want to show you a couple things. Notice those 2 white blobs there. Those are boulders standing on the surface. That shows you about trafficability. You could motor across this pretty easily because it's like completely planed off and will give you spectacular geologic access to the units within there. What do you get to see? You see these banded units, such as here. These could be evidence of ancient fluvial and lacustrine systems that were dug up by the Acidus impact. We can go back in time in a place like this by exploring the megabreccias within this area. Now we're going to be looking at these mesas. You see all these particular units in here? These are mesas within here, which carry a very important part of the geologic story. Sorry, before I do the mesas, we're going to talk about raised ridges. Throughout this area, again, this is the Nili Fossae here. There's the Jezero crater. Throughout this area that's mapped in the black box, we find these raised ridges. Erosionally resistant ridges, which are left behind after erosion. And we've mapped 2,500 of these. If you put them on a rose diagram, you'll notice that they have a slight preference for this direction, which is the same direction shown in red as the Nili Fossae. So the thought is after the Acidus impact basin, as the crust was readdressing, you had the direction of least compressive stress along which fluidized fracture zones formed. So, why do you care? Hydrothermal deposits. These would have been stimulated by hydrothermal systems where the precipitation of minerals in there could have preserved evidence of a subsurface biosphere, and that's really exciting. So, there are raised ridges throughout this area, which would be a hugely important target. These are the mesa forming areas we have. And in these, they have 3 components to them. They have a basal olivine bearing unit, which is variably altered to carbonate, which grades up into a more well-preserved volcanic unit at the top. And these are either volcanic units or were emplaced as impact melt from the Acidus impact basin. And I put this on here because the engineers have looked at this area for trafficability for Mars 2020, and that arrow is pointing to what they call the thoroughfares. So throughout these areas, we see the smooth regions between the mesas, which actually from a trafficability perspective is like a highway. So we'd be able to make good time within a human exploration of this region. This is a view of those mesas, a cross-section, olivine carbonate at the bottom boulder shedding unit, and then the crater retaining cap. And you might look at those and say, my gosh, those are dangerous. But look at the vertical scale here. This is actually one of the larger ones. It's only about 5 to 20 meters high, and most of them are quite a bit less than that. So even though they look scary, they're actually, from an exploration point of view, pretty accessible and fun to work on. There is also extensive alteration that we see from basalt through aqueous processes and leaching to create kaolin group minerals that we find in areas such as this. Again, it doesn't look interesting geologically, but mineralogically, I'll tell you that this feature and this doublet we see here is indicative of the mineral kaolinite. Resource perspective, what do we use kaolinite for? Sorry? Kaopectate, that's one reason we'll keep everyone clean. Yeah, well, I was going to say ceramics, right? But no, but it could have, it's quite an important industrial mineral, but there is kaolinite there. And then let's move on to the sulfates. Down at the bottom, southwestern corner are these stacks of, capped by the Syrtis Major lavas, is several hundred meters of layered terrain, which are sulfate bearing. And I forgot to mention here that within the olivine region, we also see serpentine. And we see this collection of olivine, serpentine, carbonate, and iron magnesium smectites together. I'm ready to move on, Ben says. Okay, sulfates, extensive, so as they're useful for our production of water. And Epsom salts for soothing the astronauts' tired feet at the end of the day. Okay, so that's how the sulfates form. So this takes us to, this is an important part in Mars geologic time. It's a playground for science. It's well resourced for the humans. I'll leave that up for the science conclusions. I think I've talked through those. And then from a resource perspective, I'll just end up here on the resources. We have the sulfate minerals, which are polyhydrated, which is magnesium sulfate with at least 4 water. And that has water resources, but also agricultural use. It's used quite extensively in agriculture. Phyllosilicate minerals, which also have largely smectite clays with exchangeable water, the olivine-rich deposits, basaltic sands, and carbonate for concrete, if we have kilns at 2,700 degrees Fahrenheit. But if we do, we've got the carbonate to work with to create that concrete. This was the rubric we put together from a Mars 2020 perspective. And then the rubric that we could put together, I say this was not done as well as I would have hoped, but for the easy landing site, this is what we could say. And then for the resource, I'm just too ignorant to have filled that out. I'll just say that. So well, happy to work with people to kind of see if we can do a better job. All right, thank you.
Did you still have one on your final data? Sorry? Did you have one on your data that you'd like to take?
One more.
Slide.
No.
Okay.
I don't think so.
Thank you very much. Our third talk of the afternoon is about Nili Fossae. And Lauren, if I can ask you to also be Vanna White and demonstrate exactly where your site is.
It's just north of what Jack just talked about. Thank you. Yeah, I'm going to be talking about Nili Fossae. And by the way, Jack, I noticed on your landing site, Nili Fossae was on there 3 times. So thank you for that. So this is the area that we're talking about. Lots of diversity going on there. This is the exploration zone. I'm mainly going to be talking about this area right here. This is a shallow crater where I'm proposing a landing site to be. Lots of resources up in this area. Lots of other exploration zones going here. I have another resource area here. What I'm not going to talk about, Hargraves Crater. Potential for a lot of science, a lot of exploration going on there. Also some pocket craters that are in this area, and looking at those close up, they have a different kind of signature than you would normally see for a crater. They're real small, they're real deep, so don't know if it's actually from meteorite formation or actually could be potentially from some other process, perhaps sublimation or something like that. On the science ROAs, this is the ROIs. This is the crater that I'm proposing for landing site. This is about 15 kilometers in diameter. It's got real shallow edges to it, so there's lots of places to actually get out of it, go other places. When I first was looking at this for a landing site, I hadn't really looked at the CTX imagery, but there's a lot of stuff actually going on here for science. You've got some black material here, probably basalt. Looks like it's covering up some other material here. Don't know what that is. There's also a fissure of material, either a dike of lighter material sticking up that didn't get covered up, or perhaps a crack in the basalt exposing the minerals underneath. You also have what looks like lots of layering in this southern region. So there's lots of things going on in this crater. Then you also have exit points which go off into some of the fossae. ROI2. The landing site crater is just south of this. A lot of things going on in here. One is you have ROI indicated here on the crater sides. There are 2 possible paths into this, both from the landing site crater, one on each end of this. This actually exits into a larger fossae. But some of the other things going on here is you have this crustal material here on top, the lighter material being exposed here. That actually turned out to be very interesting on the CRISM imagery. You have some darker material here. There are probably some clays, some other lighter materials that are popping out there. Lots of layering going on there for a geological timeline. Now if we overlay the crystal image on top of that, this is what you see. Now the thing that surprised me, and this is the thing that actually drew me to this area, my main criteria for looking for a site was there anywhere within the parameters that had water ice? Crystal image shows that it is present in this area. This is that lighter material again. You see some other indications of it down here in some lower layers. You also see some of the hydrated sulfates or perhaps clays in this region. And you see kind of this type of signature throughout this area. One of the other things I want to talk about is the landing site crater is about 800 meters below mean. The elevation here is, I put it here, it's about 1100. So we have a lot of variation in elevation and to do atmospheric studies. It's, you have a lot thicker atmosphere. There's also some peaks that you can even extend that range to some of the upper regions. This is another crater that's north of the landing site, about 30 kilometers. Some very interesting things going on in here. Again, you have this crustal material that's on top, unknown composition. You also have some lighter material. Now, the first thing that I thought when I was looking at this, it looks like there's actually material flowing out of this crater. You have very diverse set of mineralogy going on here. If we overlay the crystal image for ice, water ice, this is what you see. You see that this lighter material here shows up, but you also have all kinds of other signatures around that, indications of water ice. Going to zoom into a couple of areas here. One is right at the edge of this canyon, and also this area right here. You can see some sulfates and clays, some water ice signatures there, and particularly this brighter area right there. This is the visible light imagery. In this area here, this is a close-up of that. And this is the area that shows up with a higher concentration of water ice. It looks like sand. It may be sand that contains water ice within it, so it could be a mix there. It could be snow dunes. So Alex, if you go, take your skis, man. You also see a mixture of the material up here. It looks like perhaps some basalt mixed in with some other regolith. If we go to the other area, this is a close-up of that. Again, there's the canyon there. You have quite a diversity. I'm going to blow this up even further. This is the high-rise image from this area. You see quite a bit of stratigraphy going on here. Lots of indications. There's other stuff embedded within this. This is the material here that shows up high concentration of water ice. All of this is very, very flat. And there is a bit of lots of peaks, jumbled areas within there, but there are lots of paths through that to get to this. This is also a exit into possible entry point into this canyon from this side rather than coming from one of the other side canyons. This is one of the main canyons that comes from the landing site crater. A couple things going on here. This is some of the high-rise imagery that I overlaid here. Again, you have RSL indications on the canyon walls. You have lots of stratigraphy going on here. This is the entrance into the ROI2 that I just talked about. You also have this formation right here. When I originally thought that, I thought it looked like a flow of material. When I did the looked at the elevations between the center and the outside portion of that, I actually discovered it's about 100-meter depression. So we have something taking the material out of this, exposing the layers around that. So again, opportunity to see what process is going on there. I don't have any crystal imagery of this, so I don't offhand know what that material is, but could be sublimation or something going on causing that depression, because everything else around there is higher than that. You have some small impact craters there for opportunities to get down even further into the matrix. ROI5, this is another Fossae to the east. Again, you got lots of the layering stuff going on. The wind-blown materials in the middle of the canyon. Lots of other layering going on there for geological opportunities. Talk about the resource ROIs. Now this was the big thing that I even decided to do this with. These are the CRISM images. This is the landing site crater right there, proposed LS. Entrances into some of these other canyons we just talked about, but you can see all throughout this region there's indications of water ice, also indications of the red clay or the hydrated sulfates clays. What we don't have is, what is actually in this area if we choose that for a landing site. Could be that a landing site may be easier and more feasible if we want to tap into those resources up in a different location. We look at the bound water images. Again, lots of indication of water-containing minerals. Also see the hydrated sulfates, water ice indications. Hydroxylated silicates all throughout the region. You see quite a bit of it throughout there. And some down in this area in here. I don't have any images south of here, so I don't know when that signature changes. But again, we'd like to get more images in that area if that's where we choose to land. The Mafic mineralogy, lots of stuff going on. Quite a bit of diversity in this area right here. So again, the signature kind of changes. I don't know why that one is so much different than the others. I don't know if it's the mineralogy or perhaps the image processing in that changed it a little bit. Iron minerals. I wasn't sure really how to read this. Either you can interpret this as if blue is ferric minerals, then there's lots of indication of iron. Or it could be that we want to determine how much that actually is. ROI2, this is an area that's to the east of the EZ. Again, indications of water ice, not as strong as some of the areas we just talked about. Bound water all throughout the region. So this region has a lot of the stuff that we're looking for. Hydroxylated silicates, again, there's quite a bit more up in this region, pockets of it in this other region here. The Mafic mineralogy, lots of indication of olivine, iron-filed silicates, and again, iron signature. So got lots of resources covering a wide area throughout this region. In the rubrics, talk about the astrobiology, where you have water, ice. You typically have some kind of microbial activity going on Earth. Since this has that, of course, one of the questions we would ask is, where did that come from? How long has it been there? Was it there in the beginning when these were the seas, and this is left over from that? That would possibly answer the question of past habitability or even current habitability. You can go through the rest of this. Atmospheric science, we talked about that a little bit. Lots of opportunities for the geoscience. For site factors, water resources, yep, how's that? Civil engineering, that's kind of an unknown, at least in the landing site area. Don't know the structure of the basalt there, whether it's solid, whether it's sand. Metals, silicon resources, lots of it in that region. We would want to confirm the presence, quantity, and quality of the water ice. What form is it actually taken? Is it easily accessible? Determine what resources are available in and around the landing site area that we've chosen here. Or is there a better landing site near the resources that we already have? High-rise imagery to assess the best location for a landing site and also confirm potential egress routes out of the landing site crater, also into some of the canyon areas. So there's lots of opportunities there. This is just kind of an overview of the context. This was ROI1, ROI2, landing site crater, just kind of give you an idea of the context of that. Thank you.
Hello, there we go. Thank you very much. And for our final presentation in this session, we have Laurent Sibyl presenting on Aram chaos. And if you can also go over and point at your RO or your EZ on the map.
Okay. Don't know if this works. Right over here, near the Ares Vallis.
Thank you.
Does this work? Will you hear me? Yeah? Okay. And I'll be co-presenting with Paul Niles here, who is listed on this slide. I hope he's going to have a microphone. He's going to talk the science ROI, since our team was definitely multidisciplinary. That was our approach from the beginning, to put together some ISRU from our group at SwampWorks at the KSC, and bring together people who knew much more about the science that we did at Johnson, and Timothy Glotch at SUNY Stony Brook. And we brought in also mining expertise from UNSW Australia, the School of Mining Engineering. I'm going to talk to Aram chaos as a potential exploration zone. And we chose this image not because it represents the entire exploration zone, but it represents 3 features that are quite remarkable about this area. You have very high structures that are that lend the name chaos to the entire region, where you have collapsed areas and remnants of very large blocks. So, and then you have sulfate deposit, monohydrate sulfate deposit in this case, and at the same time you have these dark basaltic region, and they all kind of coexist based on what we have seen looking at this area. So the entire ROI is, I'm sorry, the entire EZ is comprised now of about 6 science ROI and a few resource areas that we have identified. First of all, notice the proximity of the landing site. So we actually ended up moving the landing site to satisfy this criteria, and I'll talk to you to that a little bit later. ROI 2, resource ROI 2 is further because it was where we actually had the most data, and so we wanted to look at this from that perspective to actually find out about the resources. So a perspective view of our landing site of choice. The area is relatively flat, landing site ellipse sort of about 3.2 by 2 kilometers, and the surface topography indicated in these images indicate that you can actually take advantage of the natural areas to shield habitats or equipment from actually landing craft that are going to be in that area and possibly eject places. Also, you can use natural features to put away your nuclear fission power, surface power, for radiation protection purposes. It is near the equator in the northern hemisphere, and it is definitely a low area for landing. So Paul will mention to you. I don't know if you use one of the microphones or this one.
Karaoke. All right. So one of the reasons why I really like this site is that we'll go here. So the chaos terrain is not something we would normally have thought about as a landing site for robotics explorers, but given the new, given the constraints that we have for the human missions, it opens this kind of terrain up. So the Aram chaos has a sort of stack of different sediments. It's not like extremely well studied, so and we're just sort of at the beginning stages of trying to work out this landing site. But preliminary, work that's been done has shown that there's a stack of sort of polyhydrated mineral on top of monohydrated sulfates and with basement chaos. And the geologic history was that this was a giant basin. It was filled with fill of unknown material, and that material also contained a lot of water. That water stayed in that basin for presumably a fair amount of time in order to accumulate a large enough amount, and that amount of water was discharged into an outflow channel. We also see evidence for repeated cycles of this discharge. So we know that the water came and was recharged. So the thing that's really appealing from the science standpoint and the astrobiology standpoint is that this water was in the subsurface, it was liquid, and it was there for a substantial amount of time. So you have this habitable environment that you may not have in other places on the surface, where you might just have water flowing over the surface or standing on the surface and potentially being frozen and then thawed in geologic history. So we definitely have evidence for sulfate formation, evaporite formation, which occurred presumably at later stages after the chaotic terrain first formed. So you have evidence for atmospheric preservation, or be able to study the atmosphere, aqueous processes, and significant chronological implications, which we'll get into. So this is the whole crater together. You get an idea of the chaotic terrain and the fairly obvious nature of the collapse. The red colors here are hematite detections, which are very similar to the hematite in Meridiani and Valles Marineris. So there's this linkage across the planet scientifically with this site. The first ROI shows sort of this is in the northern part. You see this sort of evaporite capping units. This is the latest stage deposition that we see. So this ROI would allow you to access a nice stratigraphic section of units and study these hematite sulfate units, would potentially link to global processes in the Hesperian. Really interesting questions about timing. The units that we see here are presumed to be much younger than the units that we see in Meridiani. So there's a question about how are these things connected across time and across space, and the overall chronology is important. So being able to take samples and hopefully get dates from them would give us a lot of information about the geologic history of Mars. So his other set of science ROIs was, basically picking ROIs in this site for a geologist is you can just pick wherever you wanted. The whole thing is a science ROI in my opinion. So this was my choice for trying to understand what was the basement unit like. So here we have this chaotic terrain, and presumably we'll be able to access the underneath part and really get a sense for what was the nature of the lake that originally formed the chaos terrain. And hopefully that would be something you could do here. You might be able to do it other places without in the crater. It's hard to know with the orbital imagery that we have. So this is where you would access the past life and the astrobiology, although that's also possible in any of the other locations. The other thing is that there might be some stuff going on in the subsurface here and elsewhere, and there's a really strong subsurface story to this crater that we'll talk about a little bit later, but we don't really have access to with the current data. And this is the crater rim, so being able to access the crater rim gives you access to the Milwaukeean terrain that was impacted, the host terrain, and the impact ejecta, presumably, so you'll be able to date the impact event itself. Give an idea about erosion and erosion processes. And then there's this channel. This is the channel of the delta of the water flowing out of the crater. And studying this, you can get an idea of the different events that occurred. You can see there's multiple events that have happened. And you get a sense for water volumes, water flow, and also hopefully water composition. This is our data coverage. See, it's pretty well covered in high-rise and Chrism, although we're going to request more. I think there's more that needs to be provided. So I'm going to hand it back off.
Okay, thank you. All right, in terms of resource ROIs, so the idea again was to locate this as close as possible to the landing site, because that concentration of the resource and that distance are the two parameters that will ultimately decide where you're going to put this if you're going to rely on those resources. So polyhydrated sulfates are noticed and observed in this or suspected based on the limited evidence that they are there. So 5 to 8 weight% was estimated. And I'll go over the ROI2 to show you from that data. And from that, based on the size of the resource field that we determined, and putting 1 meter notional depth, although we don't know if it's there during 1 meter, whether it's homogeneous or not, you end up with a 87% recovery rate based on the processing that's been done in labs. You end up with the ability of having 172 metric ton and fueling 11 MAVs, so 11 missions. Very, very low slopes across the whole region, and it seems that you can traverse it. But again, not a lot of details about what's actually there, whether it's extremely fluffy or would it actually support heavy equipment or heavy transport of resources or regolith or machines. And so there is potential for sintered road paving, for example, because we have also a basaltic sand in the area. ROI2, like I said, was chosen because of the data being looked at by Tim Glotch in that area, and it is indicative of a high concentration of polyhydrated sulfates. So rosenite and epsomite are found there. Kieserite are suspected too. I'm going to switch to the slides that show the data that he's been producing. So again, we're kind of trying to push the envelope here, trying to get the answers. So this is the nature of the team. We want the answers, and the science is saying, well, I don't have the answer, let me try this, and then I'll tell you something. So this is very informative. He's using a quantitative unmixing of the Chrism data as an approach, correcting each pixel for distortions and atmospheric effects and so forth. And so what's interesting is that he actually finds very high abundances, and we're looking for abundance maps like this, where you end up, again, this is an aerial abundance, so it's just the surface. We don't know anything that's below the surface, and that's a big part of the data being required further. So you're talking about high percentage of abundance, and so that kind of informed these water potential calculations with you end up with something around 8-9%. Even higher, in the tens of percent, close to 20 maybe. So that's where we're stretching the envelope in terms of possibility. So again, these materials evolve their water at fairly low temperatures. Here you see a partial evolution of the water because the samples were dried beforehand. I'm going to switch to an ROI3 dark basaltic region. For us, what that means is that if you find some things like that, you can start sintering the material to make structures. Sulfur-based concrete, the abundance of sulfates is also an interest in making these concretes that don't require much water. And the silicates are a source of silicon and glass ceramic. It's also a substrate for the plant growth. Rosenite is also, and kieserite are also a source of fertilizers. So, and for us, you have to find these type of concentration to consider these things ores. I mean, yes, you can have surface deposits of iron sulfates, but tell you the truth, you have to have them really, really close to where you are and where you need them to make this work. And this is why we looked at the case study of mining for the water at Aram chaos. So UNSW Australia is developing a model which they call the water extraction moss mining model. And we input some notional hardware. The hardware here is not very important other than saying that it has to perform these tasks, which drilling or excavating, processing, and then once you have the resource, you have to transport it. So these things are very important, and the water content becomes a limiting factor, but also the tool optimizes for the distance between the ROI and the landing site. And you have a target of what you want to do, which is provide enough water for a crew of 4 per day, 3.66 liter per person. So what ends up happening is that you end up with a graph that shows you the different sensitivities. For example, you have 3 concentration of water here, 3%, 5%, 7%. If you are very close to your ROI, you can actually have a minimum amount of equipment, and that gives you the close distance and the minimum amount of equipment allows you to have the flexibility and lower risk of actually acquiring that resource and being able to use it. If you go to lower percentage ROI, even if they are very close, you're going to end up having a lot of equipment, a lot of things breaking, and then next you have if you're very far away, then you end up with high risk. So that doesn't work either. That's why we were talking about this morning, where your mining system is most sensitive to the water concentration, but also it needs that geological information to say, yes, this is what we have, and this is what we have in depth. I have to speed up a little bit. The rubrics
you need to come to
to conclusion. So highest priority easy data needs are both for resource and science potential is better coverage and high resolution to resolve the topography for these equipments, and also go down in depth to find out about the geology. And this is what mineral exploration is about in mining. So you have to go down to the surface and confirm those water resources and the other resources. My conclusion slide is that you need these things, like to understand the surface roughness. Otherwise, you're not going to be able to mine anything, or you're not going to commit all that hardware that needs to be put down. Top 10 meter and deeper is definitely needed. I want to point out what we said earlier, which is to bring mineral exploration expertise. People who do this for a living, to actually look for resources and know how to have the methodology and minimal techniques that would be applicable. We're not going to do hundreds or 500 core to actually find at 100 meter deep to find out what our resources. So we need novel ideas from that from you. So thank you.
Have a safe trip.
Okay, if we could have all the speakers up now.
Mm-hmm. Do I keep this?
Keep it for the.
Okay.
I bet you get questions. Okay.
This is a special one. We get 6 people up here as opposed to 4. So it's a crowded
Yes,
field.
sure.
So actually, I wanted to start with a quick question first. The question I had for you guys is, a lot of the sites that were presented in this session are ones that are sort of veteran for the robotic landing site selection process. But one of the things that we talked about with the human science exploration, or the human science objective SAG, is what are the additional benefits, the benefits of a proximal human, my favorite phrase ever. But so what do you guys see as the benefits of a proximal human to the sites that you guys proposed? Why are they, why should we think of them as human landing sites as opposed to just the robotic landing sites?
I'll start that. Song? Hello? Testing? The song?
I think.
Did I turn it on?
I'm not sure.
Use this one here.
Testing. There we go. I want to try to answer that. I think the parameters or the requirements and the things that we're looking for are different with the robotic site. We can land a lot more accurately. We're looking for resources, not just science. So I think that changes the picture. And at least I know with some of these areas, there's a lot of resources, a lot of things that we're interested in if we're talking about a manned mission versus just a robotic mission.
Yeah, I would just say that all these sites have pretty complex geology, and being able to explore the depth of what is going on really is difficult to do with just a single rover.
I'd say, Lindsay, why is it any different than any other site, which you can only see from orbit, right? I mean, maybe compared to ones where rovers have already been, but I'd say it's no different than any other sites we're talking about. Why would a human make a difference?
I think for Hypanis and probably all of these sites, the additional size of a 100-kilometer radius exploration zone really increases the amount of diversity that can be sampled. And for Hypanis in particular, the big science questions are, was this delta indicative of a habitable environment? Did it preserve evidence for life? And was that deposited in a sea or a closed basin? And also, what's the nature of the dichotomy boundary? I think with a rover, you can address one of those three questions, but in a 100-kilometer exploration radius, we can get at all three.
Great, thank you. Ben?
This is a question for all of you. Let's say, for the sake of argument, that we expect, because we're here, that humans are going to go. And so I don't think it's fruitful for us to spend our time saying why we should send a human. We're sending a human, and that's the purpose of the meeting. So the second part that I want to say, and here is what leads to the question, there's a big disconnect between saying it's got minerals from which you could get water and it's a habitable environment. It's like a Miller analogy test to take a college board exam. The category that doesn't go with the rest of the rubric is habitable environment. And I see everyone talking about, oh, you got your habitability down here in the ground, you got your habitability up there in the cliffs. I think it's really dangerous because habitability potential is something that you evaluate on the basis of all this other stuff that we study. So I'm going to ask you to try on an idea, and that is to do a thought experiment at each of these sites and ask yourselves, what is at these sites that tells you something about the redox chemistry that can be conducted in pursuit of metabolism at those sites? Not only in pursuit of metabolism, but also in possible preservation or degradation of key chemical analytes, which would tell you it's got good or bad habitability potential. And if you would all please talk about what you can learn about redox potential at your sites, I'd be very interested.
So for the Northeast Syrtis region, the fact that you have the assemblage of minerals, which give you an indication as you go from reactant to product, you have to go through a pathway of dissolution and reprecipitation, which the conditions necessary to create, for example, the magnesite requires there to be a clement pH condition. So it has to be habitable in that sense, pH greater than 5, likely. And then as you look at the oxidation state of the minerals we see in there, we see a lack of significant indications of ferric iron in the process. So under those two conditions, you'd say the oxidation state was low and the pH state was low. So there's two indications why that was a habitable site. I could go on to other sites, but I'll let other people talk about it.
I'll let Melissa talk a little bit more about the redox, but I'd like to take another look at that question and say that the delta that we're looking at is indicative of a lot of water, standing water, and that's something different than hydrated minerals. So to infer the different chemistry which was involved just based on a hydrated mineral chrism detection, you have to then address your question of what that means for astrobiology. But when we're talking about a large body of water and a large feature on the surface, which is a delta, then that's why we made that our science ROI, and we left the hydrated minerals as resource ROIs, precisely for that reason. But I'll let Melissa take another stab.
I'll just add that as I mentioned, the CRISM data is limited at the Hypanis site, but what we do see are occurrences of iron magnesium clays in association with delta deposits, in association with other plains deposits. And so those are indicative of a more neutral water environment, more Yellowknife Bay-like waters as opposed to Meridiani-like waters. But with the limited data available, that's as far as I can comment on redox.
So I would second your thoughts about hydrated minerals not indicating water necessarily, or big bodies of water. I personally, as many of you know, don't subscribe to that. I think that the real key here is how long did the water last, and how long was it there, and was it protected from the surface chemistry? Because I think the surface chemistry and conditions may have been quite hostile to liquid water for long periods of time. I think you can get these deltas or whatever other features that you get, and they might be just very short periods of quick melting and of water flowing across the surface. So I think that for when you talk about habitability, I think from my perspective, it's how long was the water sitting there, and and obviously what was the chemistry. That'd be great to know as well. In some cases, we just don't know. And you're going to disagree.
No, I'm not going to say that's absolutely true. Duration and the duration and habitability is key, we think. It takes time. I don't know what takes time, but it takes time. We don't know when yeah, we'll both go there. But the other part of it is the subsurface environment, which we're all talking about surface environments. Why aren't we talking about subsurface environments? I did talk about the potential of subsurface environments represented by raised ridges, which could be mineralized fracture zones. Come on, that's pretty exciting, because that's the longest duration aqueous environment that's likely habitable given the temperatures and conditions being underground. Whether or not it had the biotic density to be preserved, that's an open debate, but I think we should be talking about subsurface environments and access to them.
In ROI 2 on my slide, or the science resource 2, it did show the indication that there is surface water on top of the Mesa area there, but there's also a layer down below. Those are obviously going to have different ages. So you can use that, and that's going to give you different information. But all throughout the region, there is crystal image indication of water ice, so that's readily available. We need to understand what the thickness of that is to how much that resource actually represents.
And I definitely cannot talk much about habitability, but one thing that I did notice working with science and listening to a lot of people is that there's a lack of understanding of these areas about their geological history and the formation of anything that we think may be there. Most of the data that I'm seeing, or at least that we looked at, was surface data with not much to say about why certain things are there and where do they come from. So I think the missions show that they show a lot of surprises, and so there's a lot of missing data.
So we have a question in the back here, I believe, Carol.
Yeah, so I had a question about the Nili Fossae water features. Actually, that's kind of stunning. Is there a publication on this? They have to be in severe disequilibrium with the atmosphere, which brings up the question of why are they there? Are there any morphological features associated with them? Are there RSLs or gullies? I'm assuming there aren't, because you would have mentioned those, but bringing that up. And what are its thermal properties? So it's very puzzling why they should be there.
Yeah, I agree. Why is it there? Is it a remnant of the seas, and for some reason is now just eroding away? Maybe that process has been going on for a long time, and that's just where the current state of that is. I mean, that'd be one of the questions we'd want to answer. If that's the case, can we over time actually see that eroding away? One thing in the CRISM image that you could actually see at the bottom of that canyon, where you had the canyon with the cutout portion, actually looks like glaciated activity. So something is drawing that material out of the canyon into the main canyon. You can see that all throughout the bottom.
So Carol, I think you were talking about the indications that you showed there being a water ice through the use of the 1500 nanometer spectral parameter within the CRISM database. Correct. Right. So I hate to rain on the parade. Maybe that's not the right word, but that parameter is notoriously difficult to interpret. And so when we're working with that to say, is there water ice, we want to look at the full spectral resolution. You want to see the full indication of there being water ice features there. In my experience in that area, I have no evidence of having seen that in the spectral data at the full spectral resolution. I want to encourage you to go back and look at that thoroughly, and to, once a parameter lights up, to then go and investigate it through a full spectral analysis. Because it looks really intriguing, but my experience with the 1500 nanometer spectral parameter is it's difficult to interpret. I hope that answers your question, Carol. We'd look at it more carefully.
I think John has
Yeah, and just one more thing on that real quick, and I understand what you're saying. That's why I asked the question. We need to understand what form that really is. Because is it ice, or is it in some other kind of matrix, or embedded in a mineral? Some of the other spectral images do indicate that it's more the hydroxylated silicates, or some other form, perhaps not water ice. What intrigued me is that was one of the very few areas where you could see that kind of signature in the water ice CRISM image.
So I had a question about Hypanis. Since this has been discussed now a number of times, I'm always intrigued about why it's where it is. And one of the things that struck me more recently during these presentations is the unit that you described is gray, and I think you called it Noachian buttes. And I'm wondering, that's clearly part of a more extensive unit that's been removed. Could that have provided the blocking topography that enabled the ponding behind it upslope? And how do you know it's Noachian?
Yeah, so the Noachian is an inference from the fact that these buttes are older than the surrounding plains. And the plains have been dated to be early Hesperian. So that the Noachian, the interpretation that these are Noachian crater remnants poking up above the plains. Jim, do you have? Oh, next. Okay, so so they're older than the surrounding plains. So that's the interpretation, that they're Noachian and older, and because of the stratigraphic contacts and the superposition relationships.
So it was emplaced older, but its removal occurred much later than that.
Right.
And so did the removal occur after Hypanis delta was emplaced?
So the relationship between the Hypanis delta and the buttes, I'm not sure. That would be a question for Sanjeev and Elliot, who have mapped this more extensively. But I want to go to your point about, could they be the remnants of some enclosing basin that might have meant that the Hypanis delta formed in a closed basin as opposed to a more open Crissy Sea. And that is exactly the testable hypothesis that we would want to do with our astronaut explorers. So go to those buttes, look at their stratigraphic relationships and their emplacements and relationships to each other, and see if there is a story to piece together there about an enclosing rim of an ancient basin that's mainly degraded away.
So as I'm walking up to hand this to Jim, I'll ask, do you know if the relief on the buttes today provides enough topography to have formed that blocking feature?
Do you want me to answer that?
The relief today, I don't believe it's enough if you connect the dots between them all to form the depth of a large lake that would form Hypanis, but clearly they've undergone extensive erosion, so some former, more extensive version of them, perhaps.
Is it just a quick follow-up to this? Is that okay? So do you think we'll know before we want to send humans there whether or not this is, like your major question, a local regional pond or a global ocean in the northern lowlands? I mean, shouldn't we be able to get a little more information? That's probably part of your follow-on analyses, but what do you think about that? Just both.
Yeah, I'll just say I think follow-up mapping from orbit can get us so far, but I think that, you know, determining whether those buttes are, you know, impact rim structures that could have been continuous across there, I think that's more human geologist field scale mapping.
And I'd like to add that in order to determine the extent of the delta, we'd want CTX resolution or better stereo pair coverage to actually make a digital terrain model of the entire delta, do a slope analysis along all the lobes, and figure out the actual history there.
One final question, because we have to get to our picture.
I wanted to bring us back to resources, just to end on that note. And it's maybe more for some of the ISRU experts in the room than the specific site advocates. But in general, most of the resource signatures we've seen so far, the aerial extent is understood, but we have a lot of hand-wringing about just how thick it is or how deep the unit is and so on. Now we're starting to see, at least like at Jack's site, where you've got a signature that's presenting itself in profiles, so you might be able to know how thick the unit might be, but now you have to access it from a slope. Do any of the ISRU experts have an opinion about how you would trade, you know, a known aerial extent with an unknown thickness versus a known thickness that you might have to access at a slope?
Calling all ISRU experts.
Well, I would try to answer by saying that yes, there's a lot of value in seeing exposed depth. However, in that environment, I'm not sure if you're seeing what's actually buried, because it's been exposed as well. Now these high slopes, like in that first slide on sulfates, if there is water all throughout, that's a very significant evidence for depth deposit.
I guess where I would come from the ISRU side is I would throw the question back to the geologists and basically say, under what geological context would I find a high hydrated mineral just on the surface, and then would I expect it to continue down, or would I expect a dry layer? Is the hydration a form of a change in the atmospheric water content cycle, or is it something more? So from the mining side, anything on a slope is going to be a very difficult resource to go after. So trying to figure out a mining strategy for, even if I saw the profile there, may not be as advantageous as trying to, again, think about the geological context of that resource in the first place. So it opens up that kind of debate back and forth.
So I have one follow-up, and I believe Melissa has one too. So with that sulfate deposit, the vertical profile is the impressive one to get people's attention, but we can see it spread over many square kilometers where it's much more accessible in a horizontal viewpoint, and we can just scoop it out.
And I'll just add, for the sites where a major water resource has been proposed in the sand dunes, that is based on the measurement by Curiosity at Rock Nest that there was 3 to 6 weight % water in the top scoop of sand, so the top few centimeters. What that H2O profile looks like with depth, we don't know yet, but Curiosity is on her way now to the Bagnall Dunes, on the way to the continued stratigraphy in Mount Sharp, and so I'm hopeful that we will learn more about that H2O profile with depth at the Bagnall Dunes, and also it'll be a second data point for H2O in dunes. If we don't see 3 to 6 weight % water again at the Bagnall Dunes, then we may have to do some reevaluation.
Well, it's based on 3% in the dune, 3 to 6% in the amorphous component, but that's only a partial.
Okay, so up to 3% in the dune, yeah.
Okay, I was going to ask if you actually, if you look at the Dan and the SAM instrument on Curiosity, the Dan instrument should provide a vertical profile, hopefully down to about 1 meter of water weight context. If you scooped up the surface and you saw a certain weight content of water in the soil, you should be able to try to infer, at least between those two measurements, that it's not a dry layer over. Wouldn't you be able to at least get a better feel versus just a guess?
No, because you can't tell the difference between chlorine and other hydrogen phases, sadly.
The other point, Jerry, is that we scoop the stuff up, we can run it through our system, we put it in the cup, and during all of that time, you could lose water. So.
Well, yeah, of course you're going to, but I mean
So the measurement that you make isn't necessarily the measurement that you're seeing in situ.
No, but I mean, for resource prospector on the moon, the example is we're looking at using the neutron spectrometer to try to understand the potential water content within a bulk region, and then take samples either at the surface or at the subsurface, and if you can do it in multiple locations, get a sense of what the vertical profile is between those two instruments.
So this is a perfect example of the type of synergistic conversations we enjoy people having at the break, which segues nicely to the fact that it's the break. So I have three things. We want to go outside, smile like you mean it, have your photo taken. As you pass the coffee urn, if you haven't contributed and you would like to, that would be good. And then we will start again at 3:45 sharp.